down, but now we're recording. So again, I'll ask any questions, issues, concerns, problems that you may have. All right. I can't exactly remember how we left it last time. I think I do, and I think I blew it, but sorry about that. I'll get it done today. Did I tell you I was going to put the Chapter 5 test out there, or were we going to finish these last two problems before we did so? I can't recall.
You said that you were going to put the test on there, and then today we were going to finish it, but today was going to be the day.
Yeah.
The time limit.
Yeah, well, no, but there is no time limit really, except you just would have had an extra day to work on it. The trouble is, when I was going to do that, I thought I had already done it, and then I was looking for it and couldn't find it. I said, oh, I blew it. Then I went to load it, and I didn't have the test in front of me, so I didn't know if I had the right test or not, because I've taught from several different books, several different editions and stuff, and I wasn't sure I had the right test. And I was running out of time before class started, and actually did run out of time before class started while I was looking for it. So I will try to do that this evening. I have a hopefully have a couple of office hours this evening. Let me see if anyone signed up for my virtual advising. I know they didn't this morning, but I didn't check on this afternoon because sometimes they add them late, but I don't think they'd add them this late. So while that's coming up, so I will try to get it out there. I can't recall if I have it in a format that you can see. That was my issue, and I haven't resolved that yet. Like I said, when I went out to look, there were a couple versions there, but I could not tell. Let me see if I have it. No, I don't have any advisees today, so I'm in the clear. So hopefully I'll be able to get that done, yeah, shortly after 4 o'clock today. We'll see, but so sorry that I didn't get it out there before, as I said I would. I had several classes that had things to go put out today, between yesterday and day before yesterday, and I just ran out of time and got them crossed up in my head which ones were going where. And that's why I thought I'd already put this one out there, and I was looking all over for it. I said, well, where did I put it? And then I found out, well, I must not have put it. So then I started looking for it. Said, well, which version do I do? And so that's where I ran out of time this morning. So sorry about that, but we will I'll get it out there later today. So if you're frantically looking for it, hold off. Okay. Now, one of my classes that I did this for, okay, is there someone coming in, or is that a chat? Nope, still don't have Ashton coming. Okay. One of the classes that I did want to post something for, I found out I couldn't put it under the week 6 assessment, which I was going to change the name to test 1. I can't remember if that was your class or not. Like I said, there were several that came test time this week, and one of them I couldn't because they didn't have. Blackboard is supposed to provide a little plus sign so you can add something. All they had were the wording and no plus sign, so I couldn't add anything. So I think on that one I just put it under, well, I'll have to go back and check. So if indeed you can't see it under test 1, I may have already even labeled it test 1 in week 6, but there's nothing there yet. If you can't see it there, look under messages. I'll definitely be able to get it under messages, knock on wood, but I may or may not be able to put it under test 1. I'll put the grades in on test 1, but I may not be able to put the test there if they didn't provide the little plus for me to do so. I don't know who set up these templates, but they were pretty sloppy about it. And of course, I don't like them anyway, so I'm not going to gripe. I'm afraid they'll go and fix them and make us change things, so I'm going to leave that alone. Okay, any other issues, questions? Sorry I didn't get the test out there. I'll try to get it out this afternoon. Any other issues? All right. Well, these last two problems are not on the PowerPoints. So we're just going to have to do those up. That's why I've got the whiteboard up. We're going to have to do these off my Wacom pad. And here is the first of these. Now, remember we've just talked about the integrals for the 6 basic trigonometric functions. Now we're going to put those to task. Okay, so here's example 10. Integrate from 0 to pi fourths the square root of 1 plus tangent squared this is tangent of x squared dx. Okay, now where would you begin on a problem like that? I'm sorry, I left off the squared. I said it, but I didn't write it. Square root of tangent 1 plus tangent squared x. Otherwise, that would have been an almost impossible thing to do. But with the square in there, we can do it. How would you proceed? Anybody?
Make the square root into 1/2.
Okay, now that is a good idea most of the time, especially with power functions and things like this. This, however, is a trig function, and that's not going to be. It's an okay thing to do, so we can do it. It's just not really going to be too helpful here unless you think of it in terms of that. So let's try another guess. If you're going to do that and then try to do an antiderivative of that and raise it to the 3/2 power, you still have a problem because you don't have a chain rule thing for. You would have to do a 2 tangent x then times the derivative of tangent x, and boy, that gets worse and worse and worse. So that's why if you're heading in the direction I think you are, that will actually bog you down. Anyone else, you or anyone else, think of another thing we might try? Okay, I know Andy and Brandon were in my trig class eons ago, maybe at different eons, but do you remember an identity that would come to mind? And Jordan, you too. I mean, I'm not excluding you. You just weren't in my class. I know they ought to know. Does that ring a bell? 1 plus tangent squared x, or u, or anywhere else. Now, if you are exactly right, that is exactly secant squared x. So if you can simplify, sometimes that's a good idea. So let's rewrite this as the integral from 0 to pi fourths. We don't have to change the limits any because we're still dealing with x, but then this will be the square root of secant squared. Well, let's just go on and do that here. Let's put this under a square root, principal square root, by the way. That puts this under principal square root. And what's the square root of secant squared? Secant, you got it. Secant x. And that's where I thought if you were heading that way and saw that that was the square root of secant squared, then do it. But I said, nah, you'd probably recognize that under the square root rather than raised to the 1/2 power. And that's your dx. Now, remember last time we found out what the antiderivative of this was, and it's a weird one. Okay, one that I don't typically memorize. I'll look it up if I need it. And all we have to do is look at the upper part of the page there, and it's just right above this example 10. And it tells us what that is. That is, if I can get my pen to get in the right place, that is the natural log of the absolute value of secant x, rather bizarre, plus tangent x. Okay? Evaluated from, see, the one in the book is indefinite, this is a definite, evaluated from 0 to pi fourths. Okay, so the rest of the problem is merely evaluating it. This will be the log, it doesn't write well, of absolute value secant of pi fourths plus tangent of pi fourths minus the log of absolute value secant of 0 plus tangent of 0. Alright, so let's do some evaluation now. That's the log, natural log of, anyone know what the secant of pi fourths is? Come over here to the side. Secant of pi fourths. Frankly, I don't keep that one in my head, but I do know secant is the reciprocal of the cosine of pi fourths. And I do remember what the cosine of pi fourths is. Don't you? Please say yes. Anyone? Cosine of pi fourths. Little hint, same as the sine of pi fourths. Anyone know what it is? Exactly. Now, because it's already in a denominator, where did that square root of 2 over 2 come from? It originally was 1 over root 2, right? And then we rationalize the denominator. Well, if it's 1 over root 2, then this makes the secant pi fourths just root 2. Okay, so absolute value of root 2. Plus, anyone remember what the tangent of pi fourths is? Please say yes. Tangent of pi fourths. Now remember my hint before, I said cosine of pi fourths is the same as sine of pi fourths. What is tangent of pi fourths relative to sines and cosines? The ratio identity or quotient identity. Tangent is sine over cosine. And if sine and cosine are the same value, root 1 over root 2 over 2, then the ratio is 1. Tangent pi fourths is 1. Minus the log of absolute value. Anyone remember what the secant of 0 is? Just like we did over here. Oh, I hope not. 1, you're absolutely right. This will be the log of 1 plus, anyone remember what the tangent of 0 is? Zero, yes, that was the 0. Okay, and guess what? We don't need these absolute value bars. This is the log, natural log, because that's a positive number, that's a positive number, the log of root 2 plus 1 minus, what's the log of 1? Anybody? Log of 1. Absolutely. So there's your answer. Log of root 2 plus 1. Now, they go the extra mile of calculating what that is. So on my handy dandy cell phone, which I use as my calculator now because I always have it with me and won't always have a cell phone with me, I'm going to turn it sideways to get the scientific notation, scientific calculator activated, because I need to take a square root. So on this phone, on my phone, I have to start with the inside and work my way out. So I do a 2 first, then take a square root of that, get 1.41 for blah, blah, blah. Okay, so that's okay. Plus 1 equal, and now take the natural log of that. And there's a ln key there. Take the natural log of that, and I get that it's right around, come on, pen, show up, get in place. There you go. Approximately equal to 0.88. I kind of want to just stop there. They give more digits than that. 13735,870, blah, 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 blah. They do 881. That's just as good. Okay. You got the general idea. Do you see how that works? Any questions on it? Okay. If not, I'll set my calculator down for a moment, my phone down for a moment. And if you don't have any questions, let's move on to example 11. Also not on the PowerPoint, so we'll have to do it here. And that will be this one. Find the average value of f of x is equal to tangent x okay, on the interval 0 to pi fourths. Uh-oh, SpaghettiOs. How do we do average value? Well, if you remember, the average value, I'll put AVVL just for average value because I don't know what else to call it. I don't want to write it all out. The average value is 1 over the interval. Pi fourths minus 0 is just going to be pi fourths. 1 over pi fourths is actually going to be 4 over pi. I'm just being lazy. I don't want to have to write that twice. Okay, so 1 over pi fourths is 4 over pi, and then it'll be the integral from 0 to pi fourths of that function, and that function was tangent x dx. Now, you can either look right above you on the table there, or if you prefer, you can actually work it out from scratch. Which way you want to go? Y'all are going to be doing the work, not me, so how do you want to go? Work it out or look up above and get it off the table? Anybody? Okay, let's work it out. What I'm going to do then is do this to be 4 over pi. Now you see how I got that. It's 1 over pi fourths, which is 4 over pi, okay, times the integral from 0 to pi fourths, okay, and tangent x is sine x over cosine x. We did this earlier, dx, and here's the most complicated part of that, so let's do a u substitution. That's supposed to be a let u, not a lu. Let u equal cosine x, because that's in the denominator, the more complicated position. Then du is equal to, anyone remember what derivative of cosine is? minus sine x dx. Okay, we had that earlier. Okay, well, we don't have a minus sine x dx, we have a sine x dx, so let's change the signs of both of those and make that a minus. So this will then produce, in fact, I think I'll come over here and do it. Let me get my eraser activated again and come over here and do it because I have lots of room here. This becomes minus 4 over pi, because I'm pulling out that minus sign from here, times the integral from 0 to pi fourths. Okay, and what do we have? Oh, whoa, sorry. Let's erase those for right now. Because we're doing a u substitution, let's go and change the limits too. Okay, we'll do that in just a second. That will be du, because we pulled the minus sign out already, du over u. Okay, now let's change the limits. When x is equal to 0, cosine of 0 is, anybody? 1. When x is equal to pi fourths, cosine of pi fourths, you already answered that once a day. What was that? How soon? Exactly, square root of 2 over 2. Okay? Now, okay, so if you remember, square root of 2 is 1.414, and that divided by 2 is going to be a number less than 1. So we got our limits backwards now. So what let's do is flip them, but when you flip them, you negate, and that loses the minus sign. So we go back to 4 over pi times the integral from root 2 over 2, which is, remember, is about 0.707, to 1. And we should have just gone, so du over u. And what's the antiderivative of du over u? Come on. We've been doing it over and over in this section. Log u. Absolute value u, of course, evaluated between root 2 over 2 and 1. Okay? So this will be 4 over pi times, anyone remember what log 1 is? Zero. Okay, so we won't even bother writing that down. Minus the natural log of root 2 over 2. Okay. Now, the book didn't quite do it this way, but it works out, I think, the same. So first, let's get up my calculator again. Okay. Turn it sideways so I can get my scientific calculator. And start with the root 2. So 2 square root, that's how I have to do it sort of backwards, divided by 2 equal, that gives you the 0.707 like I said it was, okay? And then we're going to do a natural log of that. That turns out being a negative number, but then the minus sign there where the flashing thing is negates that, and then multiply that by 4 and divide that answer by pi. And that gives me a number of about 441 or so, okay? And again, I'm going to approximate this to be 0.44. The book put it 441, but I don't know where they get all that significance, okay? That's the average value of that one. Now, I'm Not about to draw the picture for you, but I will show you the picture. Oh, I didn't mean to do that. And I need to undo that if I can. Okay. This is a blown up version of the little bit of the tangent function, if I can find it. Where is it? Where is it? There it is. Okay. From 0 to pi fourths, where the sine of pi fourths is 1, and you're finding the average value under that, and you did the function value, that's the area under the curve, divided by the length of the curve, and that gave you the average height of the curve, which is the average value. Okay, so that's, if to jog your memory, that's how it worked. And it does appear to be certainly something less than 1, and about 0.44 looks pretty good for what we have there. Now, that's it for 5.7. Any questions? Okay. I highly recommend you always look at the concept checks. That sort of refreshes your mind, hopefully, of what some of the concepts were that we covered in this section, and reminds you how they work. So take a look at that always. And the homework exercises begin with any of the odds, 5 through 27. They're all at Calc Chat. 9 is at Calc View. Then do either 29 or 31. They're both at Calc Chat. 29 is at Calc View. Any of the odds, 33 to 41, they're all at Calc Chat. 33 is at Calc View. Either 43 or 45. Now it says you'll need maybe a graphing utility. I don't think you will, but you might. See what it takes. They should both be at Calc Chat as well. 47 should be at Calc Chat. The slope field problem, we talked about that before. We haven't really done it, but they talked about it some earlier and now, so you can do 49 if you'd like. It should be at Calc Chat as well. Any of the odds, 51 to 57, they're all at Calc Chat. 55 is at Calc View. 59 should be at Calc Chat. It indicates you might need a graphing utility for that. Try it and see. Any of the odds, either 61 or 63, they're both at Calc Chat. 65 or 67 are both at Calc Chat. 67 is at Calc View. 69 and 71 are at Calc Chat. 69 is at Calc View. 73 and 75 are at Calc Chat. 73 is at Calc View. Going back a bit in time, 77 should be at Calc Chat. 79, you can explore doing that if you'd like. It should be at Calc Chat. And then you can do any of the odds, 81 through 85. They should all be at Calc Chat. I want to point something out to you about 81. Napier's inequality. Hey, sounds like a potential paper topic to me. Who in the world was Napier? You probably have run into him before. Why did he develop, or how did he develop this inequality? Who uses it? That kind of stuff. So there's a few potential paper topics. Hint, hint, get working on your papers. All right. Then any of the odds, either 87 or 89, they should both be at Calc Chat. And then any of the either 91 or 93, they should both be at Calc Chat. 97 and 99 are true false. They should be at Calc Chat. And 101's a proof. If you're interested in doing it, it should be at Calc Chat. All right. Now, I'm intentionally leaving out 5.8. It's a good section, but frankly, we're going to be hitting this, how to do this kind of stuff later. So I think it's kind of redundant to do it now, sort of the hard way, and then we're going to learn an easier way to do it later. So let's leave those off for now. Now that was one of the things about the test, and I think I told you that the 10th question on the test is using stuff from 5.8. So if you want to leave that one blank, you can. It won't hurt you. If you want to try it, you can. It won't hurt you to get it wrong. However, if you try it and get it right, you get a bonus point. Okay? So you decide on that question 10 on the test. The others on the test are all from sections 5.1 to 5.7. All right. Any questions then? So we're going to skip through. And by the way, there's another good set of basic integration rules on page 368. Even though we're skipping the section, it has some good stuff in it. Pay attention to it. We are skipping for sure 5.9. However, looking at 5.9, there's a handsome bust of Johann Heinrich Lambert. Okay. Never heard too much of him. However, he did do some work with hyperbolic functions. I don't particularly care for hyperbolic functions because they're, to me, so much easier to deal with their definitions, which are all exponentials. And exponentials are so neat. All hyperbolics do is give me something else that I can mess up signs with, because they are similar to sines and cosines, but they're not. And their signs sometimes are the same and sometimes not. So you always have to look them up anyway. So why not just go on and use the exponentials? There is a little blurb at the bottom of that first page that's another potential paper idea. And again, the book is great for paper ideas, but the book can't be your source. It can be source of ideas, but not source of your work. On page 374, there's another reference to some work. I, again, don't mess much with the hyperbolic, so you can sort of skip through that. Now, if you are in a field that you know they use hyperbolic functions all the time, by all means, take a look. It's not hard. It's just time consuming, and I don't use them. Okay, I just don't use them. Review exercises at the end of the chapter might give you a few more things to practice on. So if you want to, you can do any of the odds 1 through 5. This is on page 383. Review exercises for the chapter. 1 through 5, they should be at Calc Chat. 7 and 9 should be at Calc Chat. 11 should be at Calc Chat. 13, 15, 17 or 19, 21, 23 or 25, 27, 29, 31, 33, either 37, any of the odds 37 to 39, 41 or 43, 45, 47, 49 or 51, all at Calc Chat, by the way. Any of the odds 53 to 61, any of the odds 63 to 69, any of the odds 71 to 77, 79 to 83, 85 to 87, and then I think you can do 89. 91 and 93 look a little tougher, so if you don't want to try those, you don't have to. And I wouldn't even fiddle with messing with the rest of them. All right, so that's Chapter 5. Any questions on Chapter 5? Okay, Chapter 6 is differential equations, which is another course. Okay, so I say wait until you get in differential equations and do that. So now we move to Chapter 7. That's where we'll get started today. Okay, so let's get out of the screen share here and move, and still no Ashton. Okay, I haven't seen him, but I haven't been watching the screen constantly. Here's 7.1. We'll go slideshow from current slide, and let's get your names out of the way. Chapter 5 was basically integration. Chapter 7, applications of integration. And again, this is a very long chapter. We're starting with 2 very long chapters here, and Chapter 7 is a long one. 7.1, 2, 3, 4, 5, 6, and 7. We may leave off 7.7. I always did it, but when I went to a meeting when they were deciding what they wanted to put in the new syllabi, For some reason they decided, I wasn't in on that meeting, but they decided to make that an optional section. So since we're running short of time, in fact, I can't remember if they included moments in that too. 7.6. I'll check on that before we get there. But I know we do 7.1. So let's move on to 7.1. If my slide will project, advance, there it is. 7.1 is the area of a region between two curves. Okay? Now where we're going to start, well, we're going to find the area of a region between two curves using integration. Okay? Now that's any two curves. A curve up here, a curve down there, find the area between them. Now say any two curves, they can't cross. Okay? If they do, you got a problem on your hand. So as long as one function is always greater than or equal to the other function, then you can do the area between them. Okay? Now, the second of the objectives is if you have two curves and they do intersect, then use the 2 points of intersection and find the area between those 2 points. So that's what it means, find the area of a region between intersecting curves using integration, which is the area between, distance between 2 curves. It's just now you know your fixed endpoints. And we'll describe integration as accumulation process, which is an okay thing, but it's an okay thing. It's just something I don't use a lot, but we'll go over it. Okay. With a few modifications, you can extend the application of definite integrals from the area of a region under a curve to the area of a region between two curves. Now we're always, from the beginning, we're doing area under a curve in a definite integral, but now we're going to do an area between two curves. Now let's think about that. Let's consider two curves, f and g, that are both continuous on the interval a to b. Now here's curve f. It goes up like this. Curve g comes down like this. Now the good news is we're only considering it between a and b. If the b were out here somewhere, we've got problems because the curves intersected there and now the wrong one's on top. But as long as you're between a and b, and between a and b, f is always greater than or equal to g, you're okay. You can find the area between them. Okay? We'd have also been in problems if a had been out here, beyond here, because again, g gets on top and f's on bottom. That wouldn't work as well. But as long as you're on an interval that one function is always greater than or equal to the second function, you can find the area there. Now I'm going to fill in the blank just a little bit here because I think they're missing a good opportunity to do that. Now the trouble is that thing keeps fading in and out there, so if I can do it quickly, if I can get my pen down here, if we extend this line on down here, just imagine that's a straight line and this is a straight line. The area under f between a and b would be this area. Whoops, the area here. Okay, so I'm going to draw all that red. That's the area under f. The area under g between a and b would be this area, right? Well, this part down here, subtract away. In other words, it's this one minus that one. That's the area between the two curves. It's not rocket science, really. It's just a pretty straight application. Okay? So you can geometrically interpret, and this is what they're doing here, the area of the region between the graphs as the area under the graph of g, which is this area here, subtracted from the area under f, which is that entire area here. So these two cancel out, and that leaves you the area between the curves. So guess what? This is the integral from a to b, f of x minus g of x dx. Okay, that's the area of f of x from a to b minus the area of g of x from a to b. Usually this may be an easier way to solve the problem than this one. However, if this one makes it simpler than doing two integrals, do it this way. You can do it either way. whatever floats your boat. Okay? To verify the reasonableness of the results shown in that figure, which seem awfully reasonable, you can partition the interval from A to B into n subintervals. Of course, that's what we wanted to do. Each of width delta x, so just imagine there's your delta x here, between there, from x here to x there, that's your delta x. And you have a whole bunch of those. So just imagine you partition all in here and have a whole bunch of them. Okay? Then the representative rectangle between these two functions is the width of it is delta x. The height of it is the difference between f and g at some intermediate value xi. Hey, that's your integral. It's the integral of f of x minus g of x dx. Okay? Straightforward. Then take limits and all that kind of stuff. You get the same thing. But since we've already done all that, why go back and do it? But the area of that representative rectangle would be in the height and the width. Height times width. The height is always the difference between f and g, and the width was your delta x. By adding those and taking the norm of that that partition, that's what the del in two absolute values say, as that approaches 0, meaning your n is approaching infinity, then this is what you're taking. The limit of the summation from I is equal to 1 to n of this. Well, guess what? That's just an integral. The integral from a to b, f of x minus g of x dx. See, the limit of the summation goes to your integral. I wish I could get my pen to show up. Where is it? There it is. Okay. This becomes the integral from a to b. This is the difference between the two functions, and the delta x becomes dx. There it is. It makes sense any way you look at it. Okay? So here's the summation. If f and g are continuous functions, now that has to be. You can't have g or f having broken places in it. You just can't want that. You don't want it to happen. They both have to be continuous from a to b, which means you can integrate both of them between a and b. And g of x is always less than or equal to f of x for all the x's in the a to b. Not outside, but in between, it works. Then the area of the region bounded by the graphs of g, f, and g, and the vertical lines x equal a to x equal b. That is, the area is the integral from a to b, f of x minus g of x dx. Just subtract one area from the other area. In figure 7.1, the graphs of f and g are shown to be both above the x-axis. However, that's not necessary. You could take that same shape here and drop it down here somewhere. And as long as it was the same shape, the difference between f and g is a positive value. As long as f is greater than g, your delta x is a positive value. So even though they're both below the x-axis, it still works. Even if one of them's above the x-axis, one below, it still works. If they're mixed up and cross the x-axis somewhere, it still works because the area between the two curves is the same. That's what you're doing, the area between the two curves, not the area of one, a negative area. You don't have to worry with that. It all takes care of itself. Of course, the requirement is that g of x has to be less than f of x for all the values on a to b. Wow, they're going to summarize it some more. Here is the graphical. So here, the f in this range is all above. The g happens to be all below. That's okay. The difference between this is still f minus g. Okay? You don't have to worry that g is below the x-axis. It's f minus g. Since this is a negative number down here, it's minus a minus, which makes it plus. This would be the f value minus a minus, which you add this to it, and that gives you the length of that. So yes, it works out fine. If they're both below the x-axis and both of them are negative, who cares that? We're looking at that area here. F is greater than G, so F minus G is positive. Delta X is positive. There's your area. No sweat at all. So whether they're both above, they split, some below, some above, it doesn't matter, or they're all below, it doesn't matter. The same form works. Okay? Boy, they beat that in the ground, didn't they? Here's some more. Representative rectangles are used throughout this chapter in various applications of integration, so get used to them. The vertical rectangle of width delta x implies integration with respect to x, whereas a horizontal rectangle, which has a delta y then, implies integration with respect to y. Keep that in mind. That'll be helpful in many applications to follow. So finally, we get to example 1. This is on page 445. I can't believe that it took that many slides to get us a page and a half. Okay, but it did. Find the area of the region bounded by the graphs of y is equal to x squared plus 2 and y is equal to negative x between x equal 1 and 0 and x equal 1. Well, I don't really want to have to graph both of those, so what I'm going to do is just plug in the x equals 0 to this one and see what we got. Y is equal to 2. Plug it in here and you get y is equal to 0. Well, it looks like this one's on top. So this is the greater function. Okay, I'm going to put it's on top here. How about it x equal 1? This will be 1 squared plus 2. That would be 3. And this would be minus 1. Hey, hit definitely on top there. So it looks like to me this is the one on top. So let's do the math. Okay, the area between those curves would then be the integral between 0 and 1 of the difference between those two functions. That's x squared plus 2 minus a minus x, which comes out being plus x dx. Now, if you don't like not having it in the proper order, you can go back and rearrange it. It really doesn't matter. You're going to integrate it term by term anyway. So let's do the integral. If I can get my pen to show back up. Here we have it. Okay, what's the antiderivative of x squared? Anybody?
X cubed over 3.
Perfect. If our pen would write, I'd write it. Okay, x cubed over 3. Now, do you want to do the x next or the 2 next? I don't care. Anybody? I know it's going to be a plus. X, okay. What's the antiderivative of x?
X squared over 2.
Perfect. X squared over 2. And the antiderivative of 2. 2x. Excellent. Excellent. Okay, you call it. Okay. That's evaluated from 0 to 1. I'll do the 0 part later. You do the 1. That would give you 1/3 plus 1/2 plus 2. I'll do the 0 part. 0 plus 0 plus 0. Okay, I subtracted off 0. So what does it give us? 1/3 is 2/6 plus 3/6 is 5/6. So that would be 2 and 5/6 if you think of it that way. Or you could write it as, what's that? 12 plus 5 is 17/6. That's how I bet the book does it. Okay? Oh my goodness, I think they got it right. Okay. Any questions on that? Did I skip too many steps? Was something sort of fuzzy there? Everything okay? Let me see.
How did you get the plus x?
Okay. Good question. Just wanted to make sure Ashley wasn't waiting. Okay, remember it's this y, let's call that our f of x, minus this y. That's the g of x. Remember, that's what we're doing, the difference between those two. The area bounded by the graphs, the top one minus the bottom one. Okay? Well, it's x plus 2 is the top one, minus a minus x. Well, minus a minus is a plus, right? Let me write it this way. I knew I was skipping steps here. Where's my pen? There it is. That would be x squared plus 2, that's the first function, minus the second function, minus x. So this would be x squared plus 2, and minus a minus is plus x. Does that help?
Yes, sir.
Okay, good. All right. All right. Any other questions? Good question. All right, let's see how they did it. Sorry, my writing will be in the way. They drew the graph. Thank you very much. Here is the x squared plus 2. The parent function is a standard squaring function, the parabola there, but we raised it 2. That's what the plus 2, a vertical shift upward. So we knew that was really positive all in here. Here is the y is equal minus x. That's your opposite of your identity function, so that's going this way. No doubt about it, the upper function is this one, the lower function is this one. So what we're looking for is the height of this rectangle, which is the upper minus the lower. So it's x squared plus 2 minus a minus x. That's what you were asking about. That becomes a plus x. Okay? And if you think about that, this part right here is the area between the upper curve and the x-axis. This is an area down here, but that's technically a negative area. Well, you're adding that negative area to this area here, so basically that's why it becomes a plus x there, because you're adding another x down here, if you think about it that way. And you're doing that integral from 0 to 1. Now, there's nowhere in the world these are ever going to intersect, so you could have done it from any two intervals you wanted to, because this is even getting larger. This one's getting, larger. This is getting larger too, but not nearly as fast as that is. So they're never going to cross, and this one's really getting fast, and this one's going negative. So this one's increasing, that one's decreasing. Never going to cross, so this would be good if you went from -1 to 3, from -15 to 85. You could still done the exercise the same way, okay? Because they never does that g of x get greater than or even equal to. It could have been equal to, but it won't even be equal to the f of x. Okay? So anyway, that's the setup. The g of x is the minus x, the f of x is the x squared plus 2. Why they didn't write them in the other form. Notice here that g of x is always less than or equal to x of x, f of x, not just on 0 to 1, but everywhere on the whole real number system, okay? But certainly between 0 and 1. So we'll do our integral just between those two, and the area would be the height of those rectangles times the width of the rectangles. The height is the difference between f and g, and the width is the delta x, okay? So that will be x squared plus 2 is your f of x minus a minus x, that's your g of x. And when you work those out, well, they just go and say, then the area would be the integral of this delta x becomes a dx. If you went to this trouble, why rewrite it like this? I don't know. And that becomes the integral from 0 to 1 of the upper function minus the lower function dx. Okay? And when you do that, they rearranged it and did all the integration in one step. Kind of like we did, but not, well, yeah, just like we did. X cubed over 3 plus x squared over 2 plus 2x. They did reverse the order just like you did. And then when you evaluate that, you get 1/3 plus 1/2 plus 2 minus 0 minus 0 minus 0. That gives you 17/6. Just like we got. Any questions? Does that make sense? All right. Now, we're moving to an area of a region between two intersecting curves. Okay? Now, in example 1, those two functions never intersected, ever. Okay? So, but the values of A and B were given explicitly. A more common problem involves the area of a region bounded by two intersecting graphs where the values of A and B you have to calculate. And that's a pretty simple thing. Let's see it. Hold on just a minute. I haven't been talking that long, but my throat is getting very dry. I don't know if it's the change of weather or something, but I'm just having an enormous amount of drainage. So, all right. So here we have a new one. Find the area of a region bounded by the graphs of f of x is 2 minus x squared and g of x is equal to x. Well, if it's bounded by those graphs, that means those graphs have to intersect somewhere. Well, where they intersect is where they're equal to each other. So our first step here is to say, where in the world is, I'm going to change the order, where is x, that's the g of x, equal to 2 minus x squared? Okay, that's the question. This is just going to give us the bounds. This isn't going to give us anything else. Well, that's a quadratic equation, so I want everything on one side, 0 on the other side. And that's why I wrote them in this order, so I can add x squared to both sides, because I like to play around with positive leading coefficients. Also subtract 2 from both sides. Okay, so this goes, that goes, so the right hand side becomes 0, the left hand side becomes x squared plus x minus 2 equals 0. Okay, well, guess what we're going to do next? If any of you have been in my classes before, I usually say, what's the F word? Now, if that's offensive to anyone, I won't say it. But what is the F word? Do you anyone remember? Hint, hint. Factor. Now, if y'all find that offensive, I won't say it anymore, but let me know. Well, I factor by unfoiling, which I don't ever read any book calling it that. What's the only possible factorization of x squared? Well, that's x times x. Okay? Then we go to the sign of the last term before we start messing with the last term. The sign of the last term is negative. That means these two signs have to be different. One positive, one negative. It doesn't matter where you put them because x's are identical. Now, the next question is, since the signs are different, what two numbers multiply to be 2, but the difference is 1? Multiply to be 2, but the difference is your coefficient here, 1. Well, that would be a plus 2 and a minus 1. Let's check it and see. Foil it. We unfold it there. Let's check it. X times x is x squared. Perfect. X times minus 1 is minus x. Plus 2x is minus x plus 2x is plus x. And then the last is minus 2. Yes, that works. So we factored correctly. Now we solve. If two entities multiply to be 0, one or the other, or in this case, both of them have to be 0. So x plus 2 equals 0, or x minus 1 equals 0. The first one will produce, if you subtract 2 from both sides, you get x equal negative 2. Here, if you add 1 to both sides, you're solving for x, and x is equal to 1. Okay, now let's pause a moment here and consider. We have these two functions. The only two places they intersect are at minus 2 and 1. That means everywhere else they're not intersecting. That means one of those functions always greater than, or at those endpoints equal to the other one. So we have to figure out who's on top. So here's my way of doing it. I say let's pick a number between negative 2 and 1. And the first one that comes to my mind is 0. And let's plug 0 in for it here. F of 0 is 2. G of 0 is 0. Guess who's on top? F. Because at 0 it's on top, and the only place they intersect at -2 and 1, so it has to be on top everywhere in between there. Otherwise, it would have intersected somewhere else. It didn't. So this is it. So this is our upper function. That's our lower function. So what we do, we integrate from -2 to 1 of 2 minus x squared, that's the F function, minus x dx. Does everybody see that? Do you see why we did that? Any questions? All right, let's do the integration. What's the antiderivative of 2? Or if you want to do the x squared first, you can. I don't care really too much. What you want to start with? Anybody? Oh, you want to start with the x squared. So what's the antiderivative of x squared? It's a minus x squared, by the way, so it'll be a minus x cubed over 3, same as it was a minute ago, minus, I guess you want to do the x next. What would that be? Same as it was, x squared over 2. And we have the same numbers, in fact. Then we have a plus 2. Evaluating this between -2 and 1. Now that's the tougher part here, because before we had a 0 and that was so easy. Oops, oops, oops. You let me get away with it. 2x. Antiderivative of 2 is 2x. Sorry. Okay, now let's start doing the calculation. That would be a -1, we're going to do the 1 first. -1/3 -1/2 plus 2. 2 times 1 is 2. Then we're going to do a minus, which makes it a plus, a -2 cubed over 3, right? This one plugged in there. Okay. Then we have a minus, because it's on bottom, a minus, which is a plus, the -2 squared over 2. And then we have a minus, because it's on the bottom, a 2 times -2. Okay, does everybody follow what we did there? Still got some calculations to make, so let's do them. This is a -1/3. We'll leave it like that for now. -1/2, we'll leave that like that for now. We'll leave even the plus 2, though it would be easy to change. And this becomes -2 cubed is -8. So that's a -8/3. Okay, but a -2 squared is +2. +4, I can't multiply. +4 divided by 2 is 2. And then -2 times -2 is +4. Okay? Now, the good news is that -1/3 and -8/3 adds to be -9/3. That's going to be a -3. 9/3 is 3. And all the rest of it is, oops, except for that 1/2 there. Sorry about that. So this is 4 plus 2 is 6 plus 2 is 8. And then subtract a half from that. So that would be plus 7.5. Okay, so this looks like that would be 4.5, which would be, I bet the book writes it as 9/2. Let's see if that's what they got. Oh my goodness, I think they did. Okay, so let's see. Any questions on that before I start covering it up with their work? I know I'm talking fast, just trying to get as much material covered as possible. Any questions? Let's see how they do it. They draw the graph, which is perfectly fine, but you see we got the same conclusion there. We found they intersected at minus 2, x equal minus 2. I wouldn't trust the graph. I would actually do the work, find out they do intersect at minus 2, and it looks like it's at plus 1. Sure enough, that's what we got. And just as we concluded, the parabola was on top and the identity function on the bottom. So we did f minus g. They showed the representative rectangle that shows the g function on top, the f function on top minus the g function here, which happens to be negative back here, but minus and minus makes it plus. So everything's fine. Here it literally would be f minus g because that is g is positive there. But that's okay. Down here is f is being negative and g's negative, but g is more negative, so your difference is still positive. So the calculus does the work for you. You don't have to sweat this stuff, okay? The difference between those 2 points is f minus g dx evaluated from -2 to 1. X equal -2 to x equal 1, which we got up here rather than trusting the graph. But anyway, that sure makes it feel warm and fuzzy inside like we did it right. Let's see what they got to find the x-coordinates of the points. So here they go and do the same thing we did. They did the graphs, but they're not going to trust it. Good for them. Set them equal to each other. Now they set them on the other side. It's fine. And they can say minus x squared minus x plus 2 is equal to 0. Well, guess what? I don't like factoring that one. I'll change all the signs to x squared plus x minus 2 equals 0. And they just did what we did. They changed the sign by pulling it out, didn't show you that, and then factored it just like we did. And yeah, and you come out with the -1 is never equal to 0, so that doesn't enter the picture at all. But see, having that minus sign has a tendency to throw you off, okay? Don't let it happen. That's what it's there for, to trip you up. Don't let it happen. That's why I put it on the other side so you didn't have to mess with that minus sign. But here we get the x is either -2 or +1, okay? Once we've done that, the a is -2, the b is +1. So now we can go, and now they're going to start and do your delta a and the delta x and the x minus g, f minus g, doing all that. And here's what it turns out being. F was 2 minus x squared minus g, g was x, minus g, delta x. And we're going to integrate that from -2 to 1, which we found our limits to be. It's going to be the total area. And when we do that, we get minus x cubed over 3 minus x squared over 2 plus 2x evaluated here. And then, boy, they showed you how to do that, didn't they? It's equal to 9/2. Okay, this is what used to gripe. I can't think of his name now. Nice old gentleman that was in the class. He was about 79 years old. Took him last year, in 78, 79, something like that. Took all 3 of his calculus. He just wanted to keep his mind sharp. He had already had it years ago. He wanted to keep it sharp. He hated this book because they skipped steps like that. The book that we both grew up with, Thomas actually went through every step, and he loved that. This one skips steps like crazy. And they sometimes will skip the more complicated steps, but show you every one of the simple steps. Okay, it's kind of nuts to me. But that's the same thing we got, 9/2. Any questions? All right, let's move on to, they're skipping example 3, 4, and 5. So let's see if we can do those. Yeah, we've got some time, so let's do as much as we can of 3, 4, and 5. So let me clear. Anyone need this scratch anymore? That was an old problem. Okay, so let's do example 3. Maybe I can write it from here. The sine and the cosine curves intersect infinitely many times. Okay, bounding regions of equal areas, as shown in the figure. So let me show you the figure because I sure don't want to draw it. Okay, there's your sine function is the darker function, the lighter one is your cosine function. Okay, and you see in between those, you get this area here, and then you get an area there. Even though it's not the same orientation, it's exactly the same area. Okay, so let's just take it from this point to that point. See what one lobe of that intersection is. Okay, so what I did with my pen, here it is. The sine and cosine curves intersect infinitely many times, bounding regions of equal areas, as shown in that figure. Find the area of one of those regions. Okay, so the first thing we've got to do is find out where, right on the right screen here, where sine x is equal to cosine x. Now, I know that you know one of these places. In the first quadrant, where is sine equal to cosine? We did it earlier today, back in chapter 9. It's at pi fourths. Oh, wait. I do believe the Ashton's coming in. There he is. I couldn't admit him because it blacked him out. Okay, we got Ashton here. Perfect attendance again today, folks. Way to go. Keep it up. Okay. All right. Now, so welcome, Ashton. Let me see. There's other things here going on. Okay. We're in Chapter 7, Applications of Integration, 7.1, Area of a Region Between Two Curves, and we're on page 446, bottom part of the page, example 3. It's not on the slide set, so we're doing it here. We're finding the area of the region, and there's infinitely many of them, but one of the regions where the sine and cosine curves intersect. So we have to find the points of intersection. So we do sine x equal cosine x, and cleverly they do this. They divide both sides of the equation by cosine x. Now that's a little dangerous because cosine x can equal 0. But where does cosine x equal 0? At your half pi's. And that is really dangerous because we're going to include a half pi in it. But what we get there is that sine over cosine is tangent x is equal to 1. And where is tangent x equal 1? The first two places where it's equal to 1. Right of the y-axis. Okay? In other words, in the first quadrant, it's equal to 1 at one place. Anyone know where it is? We did it earlier today. This is so aggravating. Pi fourths exactly. I'm trying to draw it, but the pen keeps checking out on me. Okay. Now, that's true at pi fourths. Now, the next place it's equal to 1. Now, this is really going to be a lousy rendition of the tangent function. It basically goes like this. So there is 1 here at pi fourths, because here it's pi halves, where it's a vertical asymptote. Here is negative pi halves, a vertical asymptote. The next place it's 1 is over here. So if this is pi fourths, the period for tangent is pi, so that would be 5/4 pi. Now the problem with doing it this way is the fact here that vertical asymptote is exactly where cosine is equal to 0 at pi halves. So that's not, to me, a very satisfying way, but it does give you those 2 points where those are equal. Okay? But we're not going to use this anymore except just to find those points, and I can't get my pen to show up. So let me see if I can erase all that. Okay. So those are your points of intersection. So basically what we are wanting to do, who's on top? Okay, is sine x on top or is cosine x on top? Okay, well at pi fourths you know they're equal. But if you remember the sine function, it's going up like this while the cosine function is coming down like that. Okay, so at pi fourths, between there and 5 pi fourths, and here it does take, I'm not drawing this well, where they're going to cross again at 5 pi fourths, always sine is on top. So we're going to do sine minus cosine. Okay, so let me erase that scratch too. So you do have to determine who's on top. But you know what? What if you chose wrongly? Then you're going to wind up with a negative answer. The area is going to be the absolute value of that answer. But we're going to do it right, and we'll do the integral then from pi fourths to 5 pi fourths of sine x minus cosine x, because that's the difference. Sine's on top, cosine's on bottom. The difference between them is that. And then your dx. Anyone know what the antiderivative of sine x is? Anybody?
Negative cosine.
Perfect. Negative cosine x. And what's the antiderivative of cosine x?
Is it negative sign?
It's not negative. It's, well, the negative comes from here. The antiderivative of cosine is just sine. Remember, the derivative of sine is cosine, the derivative of cosine is negative sine. So this sign changes, that sign doesn't. Evaluate that between pi fourths and 5/4 pi. Okay. Now, where in the world are you, Waldo, when you're at 5/4 pi? Which quadrant? Do you remember? First quadrant is 0 to pi halves. Second quadrant is pi halves to pi. 5/4 pi is in the third quadrant. What is cosine in the third quadrant? Negative. Only tangent and cotangent are positive in the third quadrant. So this is going to be the minus here, and the reference angle for 5/4 pi is pi quarters. So that's going to be minus a minus, and what is the derivative, the cosine of pi fourths? You said it earlier. Square root of 2 over 2. Only it's a minus because you're in the third quadrant. Okay, so there's the first one. Minus, sine is also negative in the third quadrant. It's also negative square root of 2 over 2. Okay, now we're going to take the minus of that, which is going to make this a plus, the cosine of pi fourths, and that's the square root of 2 over 2. And then minus a minus, because minus you're doing the lower one, times the minus, that's a plus. Sine of pi fourths is also square root of 2 over 2. Boy, are you getting tired of these. Well, these are plus, so it's 4 times the square root of 2 over 2, which would be 2 times the square root of 2. Do you see that? That should be the area between your sine and cosine curves. 2 root 2. Oh my goodness, the book got it that way too. Good for them. Okay. Now, the only thing I really didn't care for in that analysis was the fact they divided by cosine, and in between this, cosine goes to 0. But you weren't really interested in it being, that ratio being continuous there. All you want to know were the 2 points where they intersected. So it was okay to do that. A little on the shaky side, but okay. All right, any questions on that one? All right, then let's move to example 4. Isn't it interesting how the easier ones they show you on the PowerPoint, the hard ones they leave off, okay? This is going to take a bit more work, or maybe a bit more thought. But the good news for example 4, this is on page 447, it's given at larsoncalculus.com. So even if you can't follow it in the book and you don't like the way I do it, you can go to larsoncalculus.com and you can see an interactive version of this type of problem. So it says find the area of the region between the graphs of f of x, which is equal to 3x cubed minus x squared minus 10x, boy I'm getting hungry, and g of x, which is equal to minus x squared plus 2x. Okay, now find the area of the region between those two graphs. Now here's where we start. We find the points of intersection, okay? And this is going to turn into something interesting because I've seen the graph, okay? It's in the book. If you've got the book, look at them. Let's find where these two are equals to find the points of intersection. So we have 3x cubed minus x squared minus 10x is equal to, this is only to find the points of intersection, equal to minus x squared plus 2x. Okay, well, we want, since it's higher than a first order equation, we want to get everything on one side, 0 on the other side, because we want to factor. So let's add an x squared to both sides. Yuck. Okay, and subtract 2x from both sides. Okay, these go to 0, which is what we wanted, and we have 3x cubed, and interestingly these go to 0, minus 12x is equal to 0, because those two all both add to 0. And that's a cubed. I said cubed and wrote a squared. Okay, sorry about that. And y'all let me get away with it. Okay. Now what would you do to that cubic equation? I'm not used to dealing with cubic equations that much. What would be your approach? What's the F word? Nobody remembered. Anyone remember? Factor, of course. Okay. Now, where do we start our factoring? Just about always? GCF, greatest common factor. So let's look at the numbers. Are there any common factors between 3 and 12? 3. So let's factor out a 3. And then let's look at the variables. Are there any common factors between x cubed and x? X. So factor out a 3x. What's left over here when you factor out a 3x? The 3's go, leaving you a 1. X into x cubed goes x squared times. 3 will go into minus 12, minus 4 times. X will go into x 1 time. Okay. Now, are we through factoring? Please say no. Can you factor x squared minus 4 any further? Please say yes. Say it again.
Yes. Yes.
How? X plus 2 times x minus 2. Perfect. Okay, let's see what these are. Now, actually we have 4 factors here whether you realize it or not. You have a 3, an x plus 2, and an x minus 4. Well, guess what? 3 is never equal to 0. So let's throw the 3 out for factoring purposes, okay? But the other one can be. X could equal to 0. And if x plus 2 equals 0, what could that make x equal? Can you do that one in your head? -2 and +2. Uh-oh, SpaghettiOs. We now have 3 places. I don't know what just happened there, but I have a thing. Is my internet okay? Am I getting garbled or anything? Okay. Something popped on the screen and then it covered it up. I don't know who does that. I think it must be Zoom. Okay. Or x equal +2. So we have 3 points of intersection. Uh-oh. Now, we don't know how these functions are reacting. So here's my little trick. I'm going to pick a number in between. We know these have nodes. They have places they intersect at those 3 places. X equals 0, x equal -2, x equals 0, and x equal 2. So let's pick a number between -2 and 0. How about -1? So let's see what f of -1 is. The pen is now writing anywhere it wants to. F of -1 would be a -1 cubed is going to be a -1 times 3 would be a -3. A -1 squared is a 1, but you got a -1, and a -1 times -10 is +10. So f of -1 is 6. Let's see what g of -1 is. G of -1 would be minus a 1 plus 2 times -1, which would be -2, and that's equal to -3. Well, guess what? Between -2 and 0, f's on top. Between -2 and 0. F's got to be on top. It's on top at -1. It has to be because they connect at -2 and 0, so it has to be greater everywhere there. So that's between -2 and 0, f's on top. Okay? Well, let's pick a value between 0 and 2. And guess where I would choose? 1. F of 1. This is really easy because you just add your coefficients. Because 1 cubed is 1, 1 squared is 1, and 1 is 1. Okay, so you just add your coefficients. 3 minus 11, that would be a -8. Add your coefficients here, g of 1, and that would be -1 plus 2 is equal to 1. Well, guess what? G's on top between 0 and 2. So now we have to, and I wish that bar wasn't in the way, because isn't that blocking anything I write behind it? Do y'all see that box in the middle? Now it's fading out. Yeah. Okay. So let's try to do it. So to get the area, and see it comes right back, to get the area we're going to start off between -2 and 2 and put f on top. So it'll be, the area would then be the integral from -2 to 0 of f minus g. So that would be 3x cubed, and then you got a -x squared minus a -x squared, which is +x squared, so that goes to 0, Oh, and then we have minus 10 minus 2 is minus 12x. I hope I did that right. Okay. Dx. And then your plus, and here when we're going from 0 to 2, we're going to put g on top. So start with that, and you have a minus x squared. Then you're going to have a minus x squared, so those go away again. And then you have a 0 minus 3x cubed, so that's a minus 3x cubed. And then you have a 2x minus 10x minus a minus 10x is plus 12x. Now, you'll notice here these two functions are exactly the opposite of each other. They're both odd functions. This different function. Neither one of the first two was a difference, was odd, but these are odd. The things you're integrating here. And let me make sure I haven't made a dumb mistake here. Yeah, exactly correct. Okay, so guess what you can do? They're covering the same interval, and well, on the opposite sides, but they're symmetric about what. So what we can do is just take one of them and double it. The book doesn't do this, but I'm pointing that out to you. We did this right at the end before, didn't we? With even, or sometime in your past you've done this. So what we're going to do is let's do this one. I like this one because it evaluates at 0 here. So let's do the integral here, and that's going to be minus 3 antiderivative x to the 4th over 4 plus 12x squared over 2, which is going to be 6x squared. Okay, and then we're going to evaluate that from 0 to 2. Okay, and we're going to double that. So I'm going to put a 2 out, and my internet connection's unstable. I thought that's what it was. I'm going to quit. Okay, did I break up some there? Okay, I quit talking math and just started talking. Okay, so we're going to do 2 times this. Okay, so let's do it. 2 times, and when you plug in a 2 here, 2 to the 4th power, it's 2, 4, 8, 16. So 16 divided by 4 is 4, minus 3 times 4 is minus 12. Plus, and then 2 squared is 4 times 6 is 24. And then when you put zeros in, everything's 0. So minus 12 plus 24 is 12. Double that, and you get 24. That's what I come up with an answer. Let's see what they got. Oh my goodness, they got it too. Now they did it the hard way. And it's not hard. They integrated this one and integrated this one. They wound up being 12 on this one and 12 on that one. Add them together, you get 24. Okay, I recognize that these were exactly opposite functions of each other, so they were symmetric. The functions up here aren't symmetric, but these two functions are symmetric about the y-axis, and they have the same interval there, so all you have to do is double them. Okay, and that's what we did, and you got 24. And of course, if you tried to just go from -2 to 2 without paying attention that you have a third 0 in there, you find out that because they are equal areas, one of them's positive, one's negative, they add to 0. And that's not a very big area. Okay, so they just warn you about that. So when the graph of two functions, well, let's see. Yeah. Remark at the bottom of the page, when the graph of function y is a boundary of a region, it's often convenient to use the representative rectangles that are horizontal and find the area uh, relating to y. When a graph of a function of y, I'm sorry, I misread that. And so you can do your areas as a function of y. And that's what example 5 is going to be. And we have about 6 minutes, right? No, we have 1 minute. Whoa, I was thinking we ended at 11:45. We don't. We end at 11:40. So I think we're going to have to stop there and pick up with example 5 next time. All right. Now, Ashton, I meant to say this because we said it before you came in. Let me say it again. I had intended, great intentions, to put the test out there last Monday, but my boss called and needed something right away, and I had to stop and do something. And later, I thought I had done it. I found out this morning I hadn't done it. I went to look for it, and I couldn't tell for sure which test, if I had the right test. So I ran out of time, and so I didn't get the chapter 5 test out there for you yet. I've got it ready. I got it right there on top. And on the chapter 5 test, there is a question. The number 10 is based on that section on inverse trig functions. We skipped that section. We skipped that section and the last section, which was hyperbolic functions. I don't really use those much. Most of the time people don't. So don't sweat those. So we're just doing the first, however, was it 7 sections? I think it was. But the last question on the test, because when I made out the test, we were doing that section. So that last question is going to be completely optional. If you leave it blank, it doesn't cost you. If you get it wrong, it doesn't cost you. If you get it right, you get a bonus point. Okay? So the last question, question 10 on the test, it's optional. We didn't do those in class. So let me give you homework exercises in 7.1. I think you can do any of the odds 5 through 9. They're all at Calc Chat. 7's at Calc View. I think you can do 11 or 13. They're both at Calc Chat. 11's at Calc View. I think you can do any of the odds 15 to 21. They're all at Calc Chat. 17's at Calc View. The reason I stopped at 21, 23 on, well, 23 is a function of y. We didn't do that. We're going to do it next time. That's on page 450. So any of the odds 5 to 9, all at Calc Chat. 7's at Calc View. 11 or 13, they're both at Calc Chat. 11's at Calc View. And 15 through 21, they're all at Calc Chat. 17's at Calc View. We'll pick up 23 after we do the next example and go on from there. All right. Okay, you can do any of those you want to. Okay. The homework is for your benefit, so you can practice doing what we did in class. Another good, yeah. So that's completely up to you. Do as many of them as it takes till you say, "Hey, I got this." Move on to something else. Okay. Move to the next section. Okay. Now remember, I don't know if y'all realize this or not. There's always they require us to put an assignment out there every week. An assignment is submit one problem. Or more than one if you're having difficulty doing them, getting the correct answer. Submit any that you have difficulty doing. But the assignment is one. Again, they're not graded, 0 points for them. It's just for your benefit. Now, the only place where it might benefit you even a little more than that is this: at the end of the term, what I do, I put little plus marks in my grade book for things that have been turned in, like homework. And if at the end of the term there's more pluses than there are blanks, okay, I don't put anything if you don't turn it in. If there's more pluses than blanks and you happen to be right on the cusp, say a 79.3, not quite enough to round to an 80, But if you turn in more homework than you missed turning in homework, I'll bump that up to an 80. So if you happen to turn out right in one of those categories, it'll benefit you to have done those. But you're not going to know it until you get there. So it's up to you whether you turn those in or not. I just wanted to remind you that's been the assignment every week. A lot of you haven't been turning them in. That's fine with me. It's up to you. You're adults. You can choose. But we are required to put up an assignment every week, so I put it up. One problem. Unless you're having trouble doing more than one, then give me all the ones that are giving you troubles. And then we'll try to go over those in class or something like them in class. Okay? All right, we've just gone over our time, but guess what? There'll be no extra charge today. Any questions? So what I'm going to do, if there are no questions, I'm going to stop sharing because I'm sick and tired of sharing. And if there are no questions, I'll end the meeting and we'll see you next Monday, right? So have a good weekend. Be safe. The virus is still going around. I have a student in one of my classes who tested positive. Fortunately, he's having a very mild case, but he's got it. One of my instructor's wife, she's got it, and she's not having a very mild case. She is really, really sick. She may be better by now, but it can hit. So please, folks, be safe. Be careful. Hope to see you Monday. All right. Bye-bye.